Okay, I think we can get started. So just a couple quick announcements. The exam for Friday is written. There are 4 questions, 75 minutes, open note, open book, closed calculator, closed internet, that kind of thing. But yeah, again, feel free to bring whatever resources you want with it. Write out a cheat sheet. You don't have to. You can just print out the notes, but the cheat sheet will be much more effective and it'll help you study. But whatever resources you want to bring is fine. Again, there are some calculations there, but they're meant to be fairly straightforward. Like, shouldn't be overly complicated. And again, it's not meant to be time limited for the 75 minutes, but you have the full time. I've had technical difficulties. My laptop died on Friday. It's getting shipped back to me today, so I'm on a loaner. So I have not finished the take-home exam yet. My plan is to finish it this afternoon and distribute it then. There's a small chance that won't happen until tomorrow. Because of that, I'll push the deadline for the take-home part of it till Friday of next week, just so you have at least a full week to finish it. Again, not that it should be that amount of time. My thinking right now, and based on the draft that I have, it'll be just 2 questions, sort of one GLM modeling thing, one ARIMA modeling thing. Reasonably open-ended, but again, depending on how motivated I get, I may split it into subparts or something, but it should be fairly straightforward. And again, once I distribute that, I will let you know and send an email out, but it'll show up just like a homework assignment. And so again, that should be the sort of the general idea, general structure of it. The in-class part should look very similar to the more theory calculation-y parts of the take-home exam, or sorry, the sample one I gave out. So if you're looking at that and you're comfortable with the material there, you should be pretty comfortable with the exam. Yeah.
In the sample one, there was like a cubic polynomial that we had to find the roots. Is that something like could be a...
No. So that was because it was take-home. You could use R and other stuff to do it. So nothing will be more than like ARMA2, so nothing more than a quadratic term at most. And again, for a lot of those, so like we derived the result for AR2, so you know what the region that's allowed for that is, so that should make it even easier then. So yeah, if you're finding yourself having to do something very complicated with a quadratic solution or anything else, there's probably a better way of doing it. So yeah, it's meant to be simple, that there's not a lot of like complicated calculations, and unreduced, unsimplified things are fine as well.
I don't know if you can answer this. Is there anything that's not time series?
So yes, there will be a little bit on GLM. Like one of the 4 questions is on GLME related stuff that we talked about, but majority of it is on the time series stuff. Yeah.
For that sort of question, it's on the practice sample midterm. It's like gives a bunch of plots, and there's like, okay, these plots are MA or AR or differencing which one is this.
Yeah.
Use these plots. When we talked about it in class, it feels like there are like certain heuristic rules that like this probably suggests MA, this probably suggests AR, but a lot of it is just like, how do you feel about it? Sort of
It's
thing.
more than how you feel about it, but no, the examples I'm giving should be fairly unambiguous.
Okay.
And if there's any ambiguity, like when I'm grading it and I look in like half the class picked one and half class picked the other, that's a problem with the question. So they should be unambiguous. They should be pretty clear cut. I'm trying to make them as clear cut as I can.
Midterm, I was like,
I know which one you're talking about. They complained last year about it too. So yeah, I tried to avoid that. They should be fairly unambiguous, but again, if in the midst of it, flag it to me and I will tell you whether it should have a clear answer or not. But I've done a pass through it to try to check for that, and I think it's unambiguous, but we'll see.
okay.
Yeah. So again, for it, if there's anything like that, it'll be similar in a way where it's only the first order we're looking at. So it will only be AR, MA, or differencing, not some combination thereof where you can't see all the things at the same time. Anything else? Okay, so this is going to be our last sort of little bit on discrete time series. Next week after the exam, we'll start on continuous time series. So we'll talk about Gaussian processes, and then we'll expand from there into space after that. So what I want to talk a little bit here, and this is not to say that this is something that you need to concern yourself with. You're not going to be doing it by hand most of the time. But I want to talk a little bit about, okay, we have these models, we've been fitting them using the Fable package, but how is that happening behind the scenes? What's actually going on? What's the problem being solved? How do we estimate those phi's and the thetas? In practice, what does that look like? Excuse me. So we'll get to that in just a second. The other thing I want to talk also is about a little bit about like predictive performance. So like how do we assess how well these models are doing? And as I sort of been hinting at and suggesting, we've been looking at within sample fit, and we have metrics for doing that. You can use RMSE. For these, sort of the standard within the time series community are these sort of model fit, model selection-y kinds of things, the AIC, AICC, BIC. They all tell basically the same story to some extent. And so if we do want to do sort of full traditional like machine learning predictive performance, we can absolutely do that. We just have to be a little bit careful about how we structure it because we can't sort of randomly leave points out. It doesn't work that way. So generally, the way that you do this with the time series is your test train split is you basically take the first 90% or whatever proportion you want, keep that as your training set, and then you hold out the remaining bit as your test set, and that's what you then try to predict for. But the point is, partly with these time series, we have not talked about it in any way, you cannot have any missing data, or if you have to impute it in some way. Similarly, we've sort of talked about at the beginning this idea of like the cross-correlation function, so that you have this other feature that you're using to predict in some ways. We talked about how to like measure that and look at the cross-correlation to decide what lags to put in. The problem with that for any kind of time series for forecasting is if I'm going to use that in practice, I need to forecast my feature as well as my model, my outcome of interest, because I need to know what that's going into the future. So that makes things a little bit complicated, or you have an artificial situation where I know one time series out to plus 12 months and one I don't. So that complicates matters, and really the way you deal with that is you model both time series simultaneously with like a multivariate model, which is beyond the scope of the course. So we do need to be a little bit careful about this. We do need to be careful about how we predict things. And the other thing that we've seen when we're doing these forecasts is like our forecast one step out is pretty good, but as soon as we go pretty far, like beyond that, it drops off very rapidly. So one of the other ways in which you can do this that I'll get to in just a second is I do this test train split, but when I'm then doing the accuracy assessment, I do one step ahead for forecasting to see how well I do for that. So I fit to the blue points, I then forecast this point, but then when I'm forecasting the second point, I include this in the fitting. So I use the real known value, not the forecasted value, because it's when you start stacking forecast on forecast on forecast that you get very wide bands and also just regression to the mean really, really quickly. So that is one of the ways to do it. The other way is just to forecast for whatever forward window you're looking at. But again, generally that needs to be a fairly narrow window because you'll not do very well unless you have some kind of seasonality or something else that's extending how far you can look. So here I just took the Mauna Loa CO2 data. We're using the tidy models. Stuff has some basic support for time series. It's not great, but it's there. So in this case, we're doing the test train split in this way. We use initial time split rather than initial split. So that's what splits it in this sequenced way as opposed to the random drawn points. So note we get the 1950s up to 1994 and then 1994 forward for the training set. But once you do that, it works in the same way. You can feed it into those models. So again, just to remind you what it looks like. So very clearly seasonal, increasing bunch of patterns. So going there. So in this particular case, like the main pattern you see primarily looking at the ACF and PACF is that increasing trend. So that's the first thing you see. But you also see, if you look at the seasonal plot, very clear year-over-year patterns. So go through, you could fit a model. What I've done here is just picked a couple. So in this case, this is sort of the model that I did by hand that got a reasonably good fit. This is one where I tried to be a little bit wrong. Like I didn't take into account the differencing on the first, like the regular bit, but it's still a reasonable model for going through things. And then I selected two of the automatic models. So this is the default one. You can turn off stepwise, so it uses a slightly different algorithm for deciding it, so it explores the space in a slightly different way. But essentially just another sort of automatically fit ARIMA model to these data. And then we have the results of how well they're doing, in that the sort of the hand-tuned model is about the same as the automatically fit model, even though they are different. I didn't show what the PDQs are of the automatically fit model, but it's not quite the same as the hand-tuned model. But they're in the neighborhood of one another. They're reasonably well fit to this data. Okay. The wrong model again is off. It's worse, but it's not a lot worse. So it's a plausible model, just not the optimal model. Okay. So we can do the forecasting. So this is the same idea. And so all that I'm doing here is just making sure that I'm passing in the testing data to the forecast function. And then to show context, I'm passing in the training data so we can see where it is. And we can zoom in. And so there are some subtle differences between these, but they more or less track the actual data. And the dashed line is that training set that I held out. So we could assess how well we're doing. And again, using the built-in tools, this is fairly easy to do. So this is the within sample accuracy. So again, it just takes the data that it has, compares the predictions to it. So we see that they're all basically about the same in terms of RMSE within sample. So there's slight variations. There's slight variations. The MAE, they sort of follow the patterns that we're seeing in the AIC, AICC as well. So the second, third, and fourth are slightly better than the top one, but not dramatically so. So point here is they tell mostly the same story, but that's all about within sample accuracy. When we look at out of sample accuracy, we see something different, which is this worse model that I picked to be wrong in some sense has a better predictive accuracy here out of sample. But again, take that with a grain of salt because I'm trying to do these far horizon forecasts. So it's trying to forecast out without using that data to train it all as I go through. So it's not bad, but note the scale of this is like 3x the scale of the within sample uncertainty. So there's a dramatic difference between these two. That is the usual kind of thing. And this is particularly the case for time series. So why it's even more important to look at these to get a fairer sense of like what is my actual error versus what is my fitted error. Because again, we're sort of overfitting in some sense. This rolling origin forecast, so we can do one step ahead forecasting. So again, it's basically just saying I predict n+1 or d+1, and then I use d+1 to predict d+2, so on and so forth. So in that case, rather than forecasting like all of the orange dots here, I'm forecasting just one step ahead at a time, and that's going to necessarily give me a better result that'll look more like my within sample forecasting, potentially. You can also change this, so you could do like 4 step ahead. Again, it depends on the context of your data, but it's sort of like how far out do you want to predict or not? How much do you want to feed in? It's up to you, but the usual thing is the farther you go, the worse you're going to do in some sense. So that choice of how far out to predict is up to you, but this is sort of the standard option, is just one step ahead forecasting to see how you're going. And in order to get that, again, it's a re-exported function from Fable, but basically it's specialized for these model data frames that you get from fitting those things together. And so what I can tell it to do is to refit, and it will then do this one step ahead forecasting. And so what we get is something that's worse than the within sample variability, but better than the full out of sample predictions. So it tells us something. So in this case, what we're seeing is that, excuse me, this is more in line with like the within sample variability because, again, those models are tuned to the actual data. So the closer we are to the data, the better they're going to look, versus this one was doing better when we were trying to forecast farther out for whatever reason. So the moral of the story is it's complicated. There's not one best approach. There's not one best thing to look at. It's really going to be depending on like your loss function of what is my goal? Is to forecast what's going to happen next month? Is it going to be to forecast what happens next year? You really need to decide what that is then, and then once you have that, you can optimize and pick the best model for that kind of forecasting that you're trying to do. So it's up to you. All of these things are built in some fashion to the package, but you have to tell it the right thing to do. There's not sort of one option that's very obvious and correct. And obviously then you similarly lack things like k-fold kind of stuff. So there's a similar lack of ability to like try to tune PD and Q across this by trying different subsets of the data. You can potentially do that by like taking different chunks, but then you're in the issue of like different regimes, whether there's what's the name of the method? Like regime change. So basically like what's happening now might be different than what happened 6 months ago or 6 years ago, that kind of thing. Yeah.
Are all of these functions, refit, accuracy, these are all Broom functions? Or?
Some of them are Broom functions, some of them are base functions, but they've been they have specialized methods for these, what are they called? MIPLs, like M tables, model tables, which are what Fable kicks out when you fit these multiple models together. So they're designed for this model comparison.
But these
kind of
aren't Fable functions themselves.
They are. So they're S3 methods. So they're exported by base or whatever. So accuracy is from Broom, but like the refit is from base or from stats. And so what they've done in Fable is they've just created a special like method for these types of objects. So this is not the standard behavior of refit. It's something that's particular to this set of packages, effectively. Yeah.
What's the meaning of ACF?
The what? Sorry?
ACF1?
I have no idea. I'd have to look up the accuracy function. It's like this is like the kitchen sink kind of thing of every possible metric you might want. I don't know what that is. Yeah, it's something.
Why do you use RMSE instead of MSE again?
So because it's on the units of RMSE are the units of Y. So it's just more interpretable. Squaring it's monotonic, so it's like ordering doesn't change. But then you just have square units. So this sort of tells us what the average error is. And so it's more interpretable in the context of, like if I told you there's a model that's predicting somebody's height and the RMSE is on the order of a foot, that means it's a bad model. But if it's on the order of an inch, then it's not too bad kind of thing. So there, again, it just tells you the units versus if I was telling you it's on the order of a foot squared, it's not obvious what that is. Like it's less interpretable, that's all.
Sure.
Okay, so for the model fitting bit, again, the main point here is just sort of illustrate the nature of the problem because the problem is only going to get worse for us because we're going to have to deal with it full speed when we talk about the Gaussian process bit. And then we'll talk sort of how it's actually done in practice for the tools that we've seen so far. So if you give me an ARIMA model, again, we'll just ignore the seasonal bit for now. We'll just simplify it and say, okay, I've got an ARIMA model with a PD and Q. What we want to do is then fit this. So basically, I have the parameters I have a delta parameter, a mean of some kind, an intercept. I have P autoregressive fees that I need to find, and I have Q MA terms that I need to fit. So that's the number of parameters that I need to estimate. And we want to figure out how we do that in practice. So for the differencing, that's straightforward. Basically, differencing just changes our data. So basically, we just difference it so that rather than having YT, I have YT prime. I lose one data point for every differencing that I'm doing. So I have a smaller data set or a larger data set. Sorry, I will always have a smaller data set of some kind. But basically, if you tell me I'm first order differencing, just difference the data. If I have second order differencing, second order difference it, take the result of that, and that's the data that you're going to fit on. And then from that, you can back out to get the Y's, T's originally from it. But there's no model fitting. There's no parameter that you need to estimate from that. It's just the data that you're actually fitting to the model. So what that leaves us is, like, again, tell me what D is. I will give you YT prime from that. And so really what I need to do is just fit an ARMA model of P and Q to that YP prime as I go through. Again, here we're going to assume the simplest case, which is that our errors are IID normal. That's generally the case because it makes everything a lot easier. If it's not normal, things get a lot more complicated. But you can have additional variations on this where you relax some of these assumptions to make it more or less complicated. Okay, so that's the basic setup. So again, what we need is just a solution that will let us fit ARMA PQ. We're going to assume stationarity. And we'll assume that it's also invertible just to make life easier for us as we go through. As we said, and again, we'll show this in a little bit more robust fashion next week, if all of the marginal distributions of a joint distribution are normal, then the joint distribution itself is also normal. Just a property of the normal distribution that makes it really nice to work with. So in this case, YT or YT prime will be normally distributed if we've met these assumptions. And so what I have then is basically just this vector of y's or y primes. We then, based on the ARMA process that you've defined, it will have a mean, it will have a covariance of some kind. So effectively what we have is this just large multivariate normal that is t dimensions. And I then need to estimate these 1 plus p plus q parameters from that. So what I can do is just write this out where, again, this mean and this covariance will be a function of the delta, the p. The delta is the phis and the thetas. So I can just fill in the entries of that covariance matrix. I can fill in the mu's from it. It'll just be one mu that's repeated across all of them, but that's what it looks like. So the goal then is to fit this as basically some kind of estimation procedure on that multivariate normal. So I have a closed form for any arbitrary arma that I can write down. It may not be a trivial one, it may be complicated, but I can write it down as a multivariate normal in terms of delta, phi, and theta. So let's take a step back, make our lives a little bit easier, and let's look at just the AR version of this and see what that looks like, okay? So for an AR1, straightforward, write it out. So we have the mean, we have the variance, and we have the autocovariance. So those are all simple functions of phi and delta and sigma squared w. Basically what I can then do is take those, plug them into that multivariate normal formula I just gave you, and I have something that I can estimate on. And so the standard frequentist approach for that is maximum likelihood. So I have a function, I have free parameters, I just need to optimize it, okay? Not trivial, not necessarily convex. It's very expensive computationally, but that is in fact what R does by default. When you're fitting an ARIMA model, is it just does a maximum likelihood estimation on that multivariate normal density. So all of this fancy stuff that we've been doing with Fable and these other packages, they are just calling the ARIMA fit model from base R, which is calling a maximum likelihood estimate. Excuse me. So that works. It's not necessarily fast, but it gets you a reasonable solution most of the time. It's not the only way to do it, and we'll show some other things that try to do it a little bit better. But one of the morals of this class that you're going to get out of this is multivariate normals are fantastically useful. They are computationally infeasible a lot of the time. Evaluating this likelihood is really, really expensive if you can't do something clever. And almost all of that comes down to evaluating the inverse of that covariance matrix. So that's really costly. So this scales on the order of n cubed. Most of our time series here have been pretty small, and that's on purpose because that makes them feasible. So if I had many thousands and thousands of points, that starts to not be something that I can calculate very quickly. Because again, for every iteration of the optimizer, I have to evaluate that full likelihood. And I have to recalculate that inverse of the covariance, which is very, very costly. So practically speaking, probably this limits around like 10,000 to 20,000. Beyond that, it starts to be infeasible without doing something clever. It just starts to bog down. So here for an AR1, there's not that many parameters. That's easier to optimize. But again, imagine like as you start getting larger and larger, there's more parameters to optimize. It's going to be slower. More iterations are going to be needed. It becomes less and less feasible. So yes, there is a closed form from the likelihood, but there is not a simple like closed form for the solution to that maximum likelihood problem. So there's not a generic solution we can write down where we can just solve it directly. We have to optimize it to get to that result. One of the clever things we can do is think about it in terms of like conditionals. So taking advantage of sort of the Markovian properties of the autoregressive bit. So basically, as soon as I take this sort of full thing and I just take yt conditional on yt minus 1, yt minus 2, all the way down to yt minus 1, once I condition on those other ones, it only really matters that it depends on yt minus 1. I can get rid of all of those other things. So what I can do is I can simplify it down to a bunch of conditional things multiplied together times then finally just one marginal at the end. So once we've done that, we can write out what each of these things are. So we'll do a little bit of an assumption here. So if like y1 is going to have mean delta and variance sigma squared w over 1 minus phi squared. Yt conditional on yt minus 1 is just a normal with mean phi plus, delta plus phi yt minus 1, sigma squared w. And I can rewrite those densities. So what I can do is just plug in each of these conditional densities into there along with the density of that normal, and that becomes my likelihood. Note there's not a large matrix to invert there. This is a much, much faster thing to evaluate than the full multivariate normal likelihood. So that's pretty quick. That's a lot easier to work with. So by taking advantage of that sort of conditional structure, we can do a lot better. So write it out, derive it. It's not super exciting. It doesn't look like strictly the same thing because it's not all the terms are not exactly the same, so we just have one weird thing that we have to add into the end, which comes from the log of y1, like the density of y1. So you get a closed form to this. Now this is something that's easier to optimize over, solve for. Again, much, much nicer to work with than that multivariate normal. Okay, so that's fine. So let's see what this sort of looks like in practice. I've simulated an AR1 process. So phi is 0.75, delta is 0.5. So sigma squared is W1. So we want to see sort of how well we recover those parameters from this data using sort of the different methods. So using something that we sort of hope is correct, the ARIMA system from Fable, what we get back is pretty close. So our estimate of AR1 is 0.76. Our estimate of the delta is 0.53. And our estimate of the sigma squared is 1. So in the neighborhood, we're pretty close. And so again, we'll treat this as sort of like, this is the right answer. If we're a little bit not careful, and we might naively think, okay, I can just estimate this with a linear model. So in that case, I have just y tilde lag 1 of y. The intercept is implicit there, and the phi there becomes the beta parameter that I want to estimate. And note what we get here are very similar answers, but not exactly the same. So in this case, I have 0.761, 0.760, 0.531, 0.532. So they're very, very close, but they're not exactly the same. Why are they not the same? No, because I've sort of taken care of that because I have this sort of the conditional thing. So I've effectively done this in some sense, except I forgot one part. I'm not taking into account this. I've essentially dropped that because what happens when I do lag of value is that y1 value becomes NA because there's no y0 value. And so what happens with the regression is it just drops that. So in essence, I'm using one less data point than I actually had to do this. So I have a slightly different likelihood that's being optimized here than what I had there. In this case, I'm dropping one small term relative to 500 points or however many points I had here. Not much, so that's why it's a wash. Basically, I get almost exactly the same answer, but not quite the same answer. So in that case, it's okay. It gets us in the neighborhood, but it is to say that we are not fitting the same model here and here because I'm ignoring that one marginal term in the likelihood to do that estimation. So not the end of the world. Works pretty well. We can fit these with BRMS as well. So if you are so inclined. So the way it works is basically very similar to the ARIMA model in Fable. You just specify this ARMA structure in your model in BRMS. So note for differencing here, that's not ARIMA, it's just ARMA. You'd have to do the differencing yourself for the value bit on the left-hand side and then feed that in and then do it. So it's not the full ARIMA, it's just ARMA, but you can have that structure. And so here what that does is basically induce the implicit covariance structure for the multivariate normal. You can look at the code. It's a little bit weird how it implements it, but it's understandable. So it's basically looking at like the lags and doing something similar to what we saw before, plus that little bit extra missing bit. And note what we get here are very similar answers. So the AR term is 0.76. The sigma term is 1.02. Note the intercept is weird. But again, you have to be careful here between how this gets reported. So what it's reporting as the intercept here is the expected value of the model, not the actual intercept term delta. So there's a relationship there, which is to say the expected value is delta over 1 minus phi. So in that case, delta is equal to the expected value times 1 minus phi. So we can go back and forth. So the true expected value, the true mean of the process is 2. And then that's basically what we're estimating here. We're off a little bit. But if I wanted to back it out and get what delta is from this, I can do it. And so in that case, we're again not quite exactly the same, but we're in the neighborhood. And again, there's the effect of the priors and some other things here. Again, this would not be my choice as a way of fitting an ARIMA model. If I had an ARIMA model, I would be using Fable or something else. But note, we're getting something that's in the neighborhood. It's not completely wrong. But there are some of these things where it's going to be a little bit shaky. So just to be aware. You can use standard diagnostics. So again, we get posterior draws from all of these things. We can do the posterior predictive checks. All of these look fine. And then we can compare our estimates from the LM, the ARIMA, and the density is the one from the posterior distributions for each of the parameters. And so note, they're all pretty similar to one another. The only difference mainly here is in sigma squared. And so this is, again, an effect of the posterior, sorry, not effect of the prior, because there's a particular prior on the intercept that's a t distribution. So it's a weakly informative one. So it's slightly biasing things. So that's why it's moving a little bit away from where the estimates are from the regression in the ARIMA model. But otherwise, they look basically the same. There's very little difference in LM and ARIMA. So they're all within the same neighborhood. So you can't tell the difference between these if I gave you the parameter estimates to say that they're fundamentally different from each other. You can similarly do predictions from this. Again, you can look at the code, but this is just the same predict stuff we've done from BRMS. So back predicting to the data we have, it fits it, we get intervals, we get all that good stuff. Where it falls down a little bit is when you try to do forecasting. And I don't have a good answer for this, but I think fundamentally it's slightly broken. Something is wrong with what it's doing because yes, it should go to this mean and that interval looks reasonable. But there should be a little bit of a gradual drop from here to there as it goes through, because it should be taking the effect of one step behind a little bit, and it does not seem to be doing that, and I'm not quite sure why. I did not bother to investigate it, but this is basically just trying to do predict with these new data sets from new points past where the data was actually observed. So something is slightly off there. I don't know what it is. I think it's not taking into account like the YT minus 1. And that may be me doing something dumb or them doing something dumb. I'm not sure. So maybe if I'd fed in, like I'd added this onto the existing data and then done forecasting, it probably would look better. But that just is occurring to me now. Yeah.
Does the MA reflect the mean sooner than the...
Even more so, yeah, because the AR, it depends on the last one and the one before that, so on and so forth. The MA only depends on the previous error, which doesn't tell you much at all. And like as soon as you start adding those errors up, they go to 0. Like they have an expected value of 0, so they just sort of go away.
So with the MA, get an MA1, you shouldn't forecast more than 1.
You're not going to get much benefit from it. You're going to be predicting the mean, essentially. Yeah. Or the mean post-differencing. Yeah. Yeah.
I have a question related to that actually. So like the plots at the beginning of this slide deck, like there the line was more like sort of following the process. So what was like the difference between that and
Seasonal effect.
seasonal method?
Yeah, that makes a huge difference because we have that longer lag term in there, the AR12 or the difference 12. That makes a huge difference of letting you persist the pattern longer. If you have a non-seasonal pattern, you're going to regress to the mean awfully quickly unless you have, like, even if you have an AR3 or an AR4, it's still going to go to the mean pretty quick. Yeah. So yeah, I could try this with, I fit in the, like, augment the original data with this and maybe it'll look a little bit better. This is more what I'd expect it to look like. So what you see is this is just the forecasting from the ARIMA model where that previous peak causes it to be pulled up a little bit, but then it quickly drops back to the mean and then persists from there. But note, like the intervals here are pretty similar to each other. So like the uncertainties are persisting the same. That's fine. It may be just a quirk of how you do the prediction matters in this particular case. And I think I screwed it up by not giving it the previous data to feed into it. Okay. So that works for an AR1. Again, we have like that one term. We can ignore it kind of. ARP, just same problem, just worse. So in this case, we can play exactly the same game. We can rewrite these things conditionally. And so what I have is each term depends on the P previous ones. And I can cycle that for as long as I can until I get to YP. Then I don't have enough stuff to condition on anymore. And I just have a marginal there that I have to worry about. And so in that case, that's what I need to deal with. And so the simple way, yes, I could do the LM type approach I did last time, and I will get maybe close. but that's going to be a function of the size of p relative to the size of n in some sense. Like, how important is this term in the likelihood? Can I ignore it or not? Is going to dictate how good that approximation is going to be. And at like a first pass, like how much does that matter? How much does that affect the likelihood? Well, if p is close to n or p is large, it's probably going to affect it a lot. If p is very small relative to n, it's probably not going to matter too much. The other terms are going to dominate. So that's sort of the hand-wavy kind of argument of, if I need a quick and dirty estimate, LM with lag p, like lag p terms in it, will get me there, will get me an approximation, but that's probably not good enough because, again, as p grows, this term is going to become more and more important, and I need to worry about that in some sense. So if we are then dealing with that, there's a number of ways of doing it. One particular way is you take the ARP process. We can write out the autocovariance. And so again, remember in that there's this sort of recurrence relationship between each of the autocovariances and the previous autocovariances. So like the autocovariance at h depended on h minus 1, h minus 2, all the way up to h minus p. We can rewrite this in terms of sigma squared. And so putting all of these together gives you this thing called the Yule-Walker equations, which basically gives us a system of equations that we can solve to try to find what those phi values are from this setup. So what that looks like in practice is basically rewriting things in that way. So we now have this capital gamma p matrix, which is basically just a p by p matrix of those autocovariances, or in other words, it's the covariance matrix. Okay? And so we have that. So that times phi is equal to the vector of the autocovariances. So again, this is the covariances along the diagonals, effectively. This is just the covariances written as a column vector. And so we can write those out. We also then, once we have those, have that the sigma squared is equal to the variance minus that transpose of that autocovariance vector times the phis times the autocovariance vector. The point is, if I can estimate this, if I can approximate it, which I can estimate from the data by calculating the variance and then the autocorrelations between each of those terms, I can then plug in a numeric value for that and then solve for it, like invert it, do it. So in that case, it's still inverting a p by p matrix, but I'm doing it effectively once. Excuse me. I don't need to iterate. I don't need to keep doing it. So that can be a lot bigger before I sort of run into bounds issues. Excuse me. So if we estimate the covariance from that, basically I'm estimating gamma p vector and I'm capital gamma p matrix, plug in the values from that I'm approximating from the data and go through it. And so this is basically just giving me a solution for what the phis will be and then a solution for what sigma squared w is. So those are all my parameters. I can solve for them directly. The only problem with this is approximating variances and covariances from the data is not super efficient. You need a lot of data to do that effectively. So in that case, again, if I only had like 20 or 100 points, this is not going to work very well for that. But again, any method is not going to work very well for 20 or 100 points. The more data I have, the more precise I can be about these things. So it does give us a method to do it. It's not ideal in all senses, but it's at least one approach that can work in this particular case. And so again, for some purely purely AR processes, this is one of the other strategies. And so you'll see for various things, one of the options you can often set for the solver is Yule-Walker, which will then basically use this method. Okay, ARMA, as you might expect, as soon as we add the moving average bit, it complicates matters. So we then again have to approximate these things. Again, just like before, it's the same thing. It sets up a set of mean and a covariance. We have a large multivariate normal. So I can always resort just to the optimizing that full multivariate normal likelihood. It's not ideal, it's not efficient, but it will always work. Okay, it can be very, very slow, but that's an option we can use. So again, this is an ARMA 2-2, but for any arbitrary ARMA PQ, I can figure out the mean is, I can figure out what the variance is, I can figure out what the covariance is, and then in terms of those parameters, plug it all in and then try to optimize that in some sense. It's nasty. The full multivariate likelihood is going to be awkward to work with. It's not going to be fun, but it's still just a brute force approach that can work. Okay. So you can try to do some conditioning, but again, the conditioning now is much, much more complicated because of those WT terms. There's a lot more things to keep track of. It's really easy to screw it up if you try to do that. So what we would like to try to do is get a method similar to what we were doing before for the AR process, but in a way where we can, so it's obvious where we get the YTs from, right? I can just lag those to get them. The WTs are less obvious. So those are the residuals of my model, but as the model changes, the residuals change, so I don't have sort of like a simple solution. But what you can come up with is sort of an iterative solution to that, where we sort of approximate them, plug them in, try it again, with the hope that that then converges over time. So example here of an ARMA 2.2, so 0.75 minus 0.5, 0.52. And here, just to keep things simple, we're going to set the mean equal to 0. So delta equal to 0, and sigma squared is equal to 1. And so again, same game as last time. Let's see how we can recover these or estimate them as we go. So ARIMA, in this case, fits things using maximum likelihood. So in this case, we're not getting as close as we were before, but we're still in the neighborhood. So again, there are more parameters to estimate. There's more complicated models. It's going to be harder to do. So again, this should be 0.75, 0.5, negative 0.5, 0.5, and 0.25. So we're within about 10 to 20% of them for most of them. And I think if we calculated like the confidence intervals based on the standard errors, we would be okay. Like all of them would capture the true value. But again, note, we're a little bit more off. It's a little bit harder. So again, it's a bit more complicated to get to this and estimate those values for an ARMA compared to just a straight AR. If we just used LM, so again, we're basically fitting the wrong model. So I just want to fit an AR2 rather than the ARMA model. Note that when we do that, we are way off. Like, as soon as you drop the MA component, you're fitting a different model, the parameters are different, everything is not the same. So this is wrong, we get the wrong answer. So one algorithmic approach to this, as I sort of suggested earlier, is what's called the Hannan-Rissanen algorithm, which is basically we're going to take advantage of sort of the invertibility. And so again, we're not going to be able to fit an AR infinity model, but normally what we see is that those phi values have to get smaller and smaller and smaller as we go. So in order to take advantage of that, we will fit a high order AR model that will give us an approximation of our ARMA model. And once we have that, that will let us approximate the Y hats by looking at the residuals of that model. We will then take those residuals, feed them into a model where I'm now auto-regressing on the Ys and the residuals to get my YT minus whatevers and my WT minus whatevers. Fit a new model. That will get me a new model with new residuals. I will replace the residuals with those and then iterate on those. And then sort of, again, hopefully after a period of time, it will converge in some sense, and then I can stop. So that's exactly what this is suggesting. So use the AR model to estimate values of the unobserved WTs. So basically, I'm getting the high order AR, get the residuals. Those are the WTs. Then I'm going to regress YT on lagged YT and lagged WT that I just estimated, or the WT hats, the approximate ones. Get a new model, get new residuals, update the WTs, repeat. So first step, so one of the base functions in stats is AR-MLE. It's a maximum likelihood estimate of AR models. One of the nice things for it is you can just give it an order max, and it will fit a model up to that order, but it will drop them to make it simpler if it can. So in this case, I ask for an AR-MLE of order max 10, and it gives me order 5, because basically after that, the fees are pretty small. We can't distinguish them from 0. So it does sort of an iterative thing of doing that. Sorry, I don't know what's driving my allergies insane today. It was fine in the last class. So we get some estimate of those. And note, again, these are not the actual AR terms that we should have seen in the model before. But again, we're fitting a different model because it's AR5 now. Similarly, if you just wanted to fit a higher order one with Fable, that's fine. So I'm fitting an AR10 here, plugging it in. Note we get similar values, but not quite the same because, again, it's a different model. But note, excuse me, as soon as we get above AR5, those phi values are very, very small. They're having a relatively low contribution to the overall thing. So in that case, that should be good enough to say I could cut this off arbitrarily and pick something lower order. So that's my first pass. Once I have those, what I'm going to then do is look at their residuals. So at this point, if I've captured everything, the residuals should just be IID, no structure in them, nothing going on, which is what we see. There's no pattern there. I'm happy with that. And so I'm going to now take these as my WI hats, so my estimates of those error terms. And so basically that's what I'm creating here, a column in the data set called W hat, basically by just taking the residuals from that model we just looked at. Once I have that, I am going to then fit a model where I basically have the appropriate ARMA structure to it. So the AR2, so lagged on Y hat 1, Y hat 2, or sorry, Y1, Y2, and then I'm lagging on the W hats that I just created, 1 and 2. So now this is an ARMA 2.2 model. So note, this has the same problem we talked about with the AR process before. We're ignoring some of the terms in the maximum likelihood. It's not exactly the right model. But again, the general idea is, for the most part, that error is relatively small overall. This is going to get us in the neighborhood of a correct answer. Yeah.
But you're also here lagging on something that you're using something that you've predicted to make.
Yeah. So it's an estimate. And so that's the usual iterative solution kind of thing of, this is not quite right, because again, I would need a truly like AR infinity model to actually properly specify. We do reasonably well. And so again, it's sort of like any kind of approximation. I'm just truncating at some point saying the error is small and I don't care. So, and so note, just doing this alone has done not bad, right? Our intercept is basically 0, which it should be. AR1 is 0.75, AR2 is about negative 0.5, theta 1 is about 0.5, theta 2 is about 0.25. So we're in the neighborhood. We're not exactly, and there's more error here than what we were getting with the ARIMA model, but we're close. So we can just iterate this. So in this case, took the LM2 model, calculated its residuals, plug them into a new LM model called LM3, and maybe a little bit better, maybe not. Again and again. And so again, you can keep going. I stopped at this point because it's not much point of looking at it, but you can see that you could iterate this, and until you sort of stop getting better, you could call it a day. And how you decide on that could be about like the sum of squares of the residuals, the AIC, some other criterion, or you could look at the parameter values and see that they're not changing very much and decide that that's the end. But again, some kind of stopping criteria could be there. And again, I can't offer you any kind of guarantee that this will necessarily converge. But you can see why this should sort of be getting better overall as we're getting a better approximation of the model. Our our W hats should be getting closer and closer, and that error should shrink as it goes.
If you go back to the slide, I'm noticing at the bottom, we're slowly deleting observations due to missingness and losing degrees of freedom here. So like on this slide, we
Yes.
we lose a couple of degrees of freedom. Those degrees of freedom are because the W hats.
Because of the W hats of the Ys, yes. Mm-hmm.
Something previous, so
Yeah.
we're losing those degrees.
And there's probably a way of being careful about this where you might not have to do that. I'm just being like the naive implementation of the algorithm. Yeah, that's a good catch. So yeah, that's affecting things a little bit. We're losing some data, but not a lot.
If we don't have a lot of data, then
That could potentially be problematic, yeah. So I'd have to think about it carefully if there's like a way we could not have that happen. I think this is just because of the lags. Each time we do it, we're introducing in essence, we're introducing 2 new NAs in the W hat column each time we do this, which is something we'd like to avoid. Yeah.
Dumb question. Why do you care what these degrees of freedom are?
It's just a measure of the data in the thing. So like there's a whole bunch of theory if you go back to like linear models. It's sort of about your budget to estimate things. And so degrees of freedom are sort of the budget you have with the model, and it's based on the amount of data you have. And so the more parameters I estimate, the fewer degrees of freedom I end up with at the end. Because again, at some point, if I have p bigger than n, I can't really do that. So it describes the budget in some sense, but that's also something that shows up in a bunch of places like the likelihood, the AIC, other kinds of things, and it just sort of talks about relative trade-offs of the amount of data you have and the model complexity, that kind of thing. It's a crude tool because it's not necessarily like you can have models with similar degrees of freedom that have very different flexibilities. So one is more likely to overfit or underfit, but there's different kinds of things. And I think it's gone out of fashion a little bit. This is a big thing in like frequentist literature for linear models in the like 80s and 90s about like measuring all of these different kinds of models and what is the effective degrees of freedom of it. I don't see that so much anymore. People don't care as much. But often those things also then go into like the tests that you do for like the F-test, the model fit, that kind of thing as well. Yeah.
What exactly is the benefit of this over like the other method? Is it just like computation more efficient?
Yes. This is very cheap to fit. Versus again, the straight multivariate normal maximum likelihood estimate is infeasible most of the time. Yeah. Like we can write it down, but that doesn't mean we can solve it effectively. So one of the things we'll actually talk about down the road when we're talking about the spatial models, where it's a little bit more explicit, is there's an entire cottage industry of methods that are tricks like this. So basically, how can I avoid having to evaluate the full multivariate normal likelihood? And a lot of them come down to like these conditioning tricks, like how do I condition on things in a nice way? So Alan Gelfand, who retired, who did a bunch of stuff in spatial stats, a number of his big papers are around different tricks about making this computationally feasible. So it's an approximate solution, but the alternative is not having a solution at all. Like just you couldn't get there. So again, this is not what ARIMA is using. It's using a maximum likelihood tricky thing. You can take a look at the documentation for the ARIMA fit in BaseR to see how they do it, but that's a variation on a maximum likelihood approach. So this is just an alternative just to sort of see again how you might do it, another way of doing things. BRMS can also fit full ARMA models as well. So again, in this case, I'm fitting it. I'm just also specifying that here I don't want the mean, just to sort of explicitly not have that parameter estimated. And note, when it does that, it does a reasonable job. So we're getting around 0.75, around negative 0.5, 0.5, 0.25. Again, not necessarily better or worse than the ARIMA model. The only difference here is because it's Bayesian, we have the full posterior draws. And so there's the fun games we can play with that. But again, there's not a huge advantage to that in this particular circumstance for these models. Chains, comparisons of these parameters from what we're getting. So again, this is HR is the effect we got from that Hannan-Rissanen model. So again, note they're all similar. There are some discrepancies. They do give us slightly different estimates, but they're all pretty small differences between them, all within the standard errors or within the posterior credible intervals for these predictions. We could do predictions as well. It suffers from the same thing as before. And again, I think if I were to tweak the new data that I'm feeding in, we'd get a slightly better thing. But again, it will be the same idea. It's going to crash to the mean very, very quickly. So it's only a very slight discrepancy in terms of that decay and then going from there for what it is. And I didn't put in the actual forecast here. I didn't pull it here, but if you are interested, one of the functions in BRMS is you can show the stand code. So you can pull it up, you could take a look at it. It's fairly readable in terms of figuring it out. It uses an approach that looks very similar to the Hannan-Rissanen method. So basically, you have these latent parameters of the W hats that you're estimating. And then so you figure those out by subtracting and basically calculating the residuals as you go. And then you iterate through this. So again, it's doing that by also avoiding the full multivariate normal likelihood. You absolutely could implement it that way with the full multivariate normal likelihood. But just like anything else, the Bayesian method doesn't make that better for you. It doesn't improve things there. Every iteration of the posterior sampler will then have to invert the normal distribution, which is super expensive. So you then pay that cost. It's very, very slow to go through that and go through it. So again, this is an approach that simplifies that, gives you a more efficient way to get there by virtue of the fact of taking this conditioning to get the simpler marginals and the simpler conditionals to draw from and then get you to the final solution. So something that is worth looking at how it's implemented a little bit, because this is one of those things, if you do it wrong, it makes the problem not work, versus if you reparameterize and set it up in the right way, it does work. And where this is leading is basically next time when we talk about the Gaussian process models, we don't have this conditioning trick anymore because it's not discrete. There's not these sort of simple Markovian structures. So it's the difference between what's called a Markov random field versus a Gaussian random field. And so now we have the full multivariate normal. We have to deal with that. It's still simplified. It's still parameterized. There's still a few parameters that we need to worry about, but we still have to learn those. And in order to learn those, we need to evaluate those multivariate likelihoods over and over and over again, which is expensive. So a lot of that will then be about the tricks around that, how to implement those effectively, what can we do. But as soon as we move out of the discrete space, there are a lot fewer of those tricks that we can count on and make use of. Okay, that was quicker than I expected, but that's fine. We'll